Tonight, we're going to talk about the most ambitious thing our species has ever seriously tried to do: sending humans to Mars. Actually put people on the surface, living there, breathing recycled air, eating food grown under artificial light, with a red sky overhead and Earth just a pale dot somewhere in the darkness. We've been talking about doing this for over 50 years. And somehow, despite all the technology, all the money, all the plans and timelines and press conferences, we still haven't gone. And the reason why is not what most people think. It's not a lack of will or funding. It's that every time someone actually sits down and works through the physics, the biology, the engineering, and the mathematics of what sending humans to Mars actually requires, the problem gets harder. By the end of tonight, you're going to understand exactly why Mars keeps slipping away from us, why every solution creates two new problems, and why the hardest part has nothing to do with getting there. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first thing you need to understand about Mars is why we want to go there in the first place. And the reason is simpler than it sounds. Mars is the closest thing to another Earth that exists within reach. It has a day that lasts 24 hours and 37 minutes, almost exactly the same as ours. It has seasons because its axial tilt is about 25 degrees, similar to Earth's 23.5. Water ice exists at both poles and in the soil. There are ancient river valleys carved into the landscape, evidence that liquid water once flowed across the surface billions of years ago. At the equator during summer afternoons, the temperature can briefly creep above freezing. Mars is not hospitable, but it is, by the standards of everywhere else we might try to land a human being, the least catastrophically hostile option available in our solar system. That qualification matters. Because once you start understanding what Mars is actually like, the idea of sending people there stops feeling like the obvious next step and starts feeling like a problem so deep it reshapes how you think about space exploration entirely. The average surface temperature on Mars is around -80 degrees Fahrenheit, or -62 degrees Celsius. The atmosphere is roughly 100 times thinner than Earth's, composed almost entirely of carbon dioxide. You cannot breathe it. You cannot stand in it unprotected. Without a pressurized suit, the low atmospheric pressure would cause the moisture in your eyes and mouth and lungs to boil not from heat, but from the absence of pressure. It's the same physics as opening a carbonated bottle. Dissolved gases come out of solution when the pressure drops. In your body, those gases are in your blood, your tissues, your synovial fluid. They form bubbles. You would lose consciousness within seconds and be gone within minutes. The surface is soaked in ultraviolet radiation because the thin atmosphere offers almost no protection, and Mars has no global magnetic field to deflect charged particles from the sun. Dust storms can grow to envelop the entire planet for months at a time, blocking sunlight, coating solar panels in fine red particles, and creating static electricity that damages equipment. The soil itself is permeated with perchlorates, a class of compounds that are toxic to human biology if ingested or inhaled in significant quantities. Mars was not built for us. Nothing out there was. None of this is new information. Scientists have known about most of these conditions for decades, confirmed in detail by the Viking landers in the 1970s and refined by every mission since. But knowing what you're up against and actually solving the engineering problems those conditions create are very different things. And here is where the story gets complicated, because sending humans to Mars doesn't involve one hard problem. It involves a series of hard problems that are deeply interconnected, where solving one often makes another worse, where the solutions have costs that ripple through the entire mission architecture, and where the margin between a successful mission and a catastrophic one is smaller than most public discussions acknowledge. Let's start with the journey itself. At its closest approach, when both planets are on the same side of the Sun and lined up in what astronomers call opposition, Mars is roughly 34 million miles from Earth. At its farthest, when they are on opposite sides of the Sun, the distance stretches to around 250 million miles. Those numbers shift constantly because Earth and Mars are both moving, orbiting the Sun at different speeds, so the geometry between them is never fixed for long. More relevant than any single distance figure is the travel time. Getting to Mars using the most energy-efficient trajectory available, called a Hohmann transfer orbit, takes between 6 and 9 months, depending on where the planets are positioned relative to each other when you launch. This isn't about building a faster rocket and pointing it directly at Mars. The Hohmann transfer works by launching from Earth orbit into an elliptical arc that intersects Mars's orbit. You're coasting through interplanetary space, falling outward from the Sun along a trajectory shaped by gravity rather than by continuous thrust. The trajectory exploits the existing velocity of Earth in its orbit, adding just enough energy to reshape the orbit so that its far end reaches Mars. It's efficient because you're working with orbital mechanics rather than brute forcing your way through space. Faster trajectories exist in principle, using more fuel to power more direct paths. But the rocket equation makes these increasingly impractical as you push for higher speeds, and fuel is the central problem of everything in space travel. The fundamental equation governing all rocketry is called the Tsiolkovsky rocket equation, derived in 1897 by Russian scientist Konstantin Tsiolkovsky. It describes the relationship between how fast you want to go, how much fuel you need, and how heavy your spacecraft is. The relationship is exponential and unforgiving. If you want to go twice as fast, you don't need twice as much fuel. You need dramatically more. Because fuel has mass, and carrying more fuel means carrying more mass, and accelerating more mass requires more thrust, and more thrust requires more fuel. The spiral is relentless. Every kilogram you add to a spacecraft requires additional fuel, not just to accelerate it, but to carry the fuel that carries it. The Tsiolkovsky equation is elegant in its mathematics and merciless in its implications. You calculate the total velocity change your mission requires, the quantity engineers call delta V, and then you work backward to determine what fraction of your vehicle's initial mass must be propellant. For missions within Earth's immediate neighborhood, like reaching low Earth orbit, these ratios are demanding, but achievable. Getting a kilogram of payload to orbit requires roughly 80 to 90 kilograms of vehicle and propellant on the launch pad. Now, extend the mission to Mars and back. You need delta V to leave Earth orbit and enter a transfer trajectory toward Mars. You need delta V to slow down when you arrive and enter Mars orbit, or to directly enter the Martian atmosphere. If you're landing people on the surface, you need delta V to manage the final descent. If the crew is coming home, you need delta V to launch off the Martian surface. you need delta V to leave Mars' orbit entirely and enter a transfer trajectory back toward Earth. You need delta V to slow down and enter Earth's atmosphere safely at journey's end. Every one of these maneuvers must be fueled. The fuel for each stage has to be carried by the previous stage. A rough estimate for the total mass that needs to be positioned in low Earth orbit before a crewed Mars round trip even begins runs into the range of several hundred metric tons, depending on mission architecture and propellant choices. That's the mass in orbit before departure. Not on Mars. Not landed anywhere. Just staged in space, waiting to go. Building and launching that much mass requires multiple heavy lift launches over potentially months of effort. Complex orbital assembly operations, the kind of sustained infrastructure and operational tempo that has never been demonstrated for a crewed deep space mission. The Apollo program cost, in today's money, somewhere around $250 to $300 billion. That brought 12 humans on the moon across 6 landings, with the longest single surface stay being about 3 days. A Mars mission would take approximately 3 years. The financial comparison isn't perfect because technology and context differ, but it gives a sense of the gap between anything humans have previously accomplished in space exploration and what going to Mars actually demands. That brings us to the launch window problem, which shapes the entire mission timeline in ways with profound downstream consequences. Earth and Mars orbit the Sun at different speeds. Earth completes a full orbit in 365 days. Mars completes one in 687 Earth days. This difference means the geometry between the two planets is constantly changing. The optimal launch window, when the planetary alignment allows an energy-efficient Hohmann transfer, only opens once approximately every 26 months. These windows are not all equally favorable either. Due to the slight eccentricity of Mars's orbit, some launch windows are more efficient in terms of fuel requirements than others. The windows repeat on a roughly 26-month synodic period, which is the time between consecutive return of similar planetary geometries. Miss a window, and you wait over 2 years for the next one. This has an implication that changes the entire character of a Mars mission. When a crew arrives at Mars after 6 to 9 months in transit, they cannot simply turn around and leave when they're ready. The orbital mechanics won't allow it. The launch window for the return trip has a specific timing based on where Earth and Mars will be relative to each other. After arriving through one launch window, the crew must wait on Mars for approximately 14 to 20 months before the planets align favorably for a return trip. Total minimum mission duration for a round trip therefore runs roughly as follows: 6 to 9 months traveling to Mars, 14 to 20 months on the surface waiting for the return window, 6 to 9 months traveling back to Earth. Add it together and you're looking at a minimum of around 3 years, under favorable circumstances, with nothing going wrong. Any significant delay on Mars, any missed launch window due to equipment problems or mission adjustments, extends the stay by another 26 months. 3 years is not just a long time in the abstract. It is the core driver of everything that makes this mission so fundamentally difficult. Because the human body was not designed for 3 years of exposure to the space environment and the Martian surface. And the machines that keep the crew alive were not designed to operate for 3 years without maintenance, resupply, or the possibility of rescue. Every challenge that follows from this point is downstream of that 3-year commitment. You cannot engineer your way around it without fundamentally changing propulsion and trajectory architecture in ways that don't exist yet. You accept it as given, and you spend years working out what it actually means. Every day, a human being spends in microgravity. The body begins to change in ways that have been carefully documented across decades of International Space Station research. Bone density decreases. Bone is living tissue that constantly remodels itself in response to mechanical stress. When you walk and carry weight against Earth's gravity, your skeleton experiences those forces and responds by maintaining its density. Your body dedicates cellular resources to keeping bones strong because the bones are being stressed, and stressed bones need to be strong. In microgravity, there is no mechanical stress. The body interprets this as a signal that it doesn't need strong bones anymore and begins the process of breaking them down. Calcium released from bones enters the bloodstream and is eventually excreted, exiting the body in urine. This happens at a rate of roughly 1 to 2% of bone mass per month. Astronauts on 6-month International Space Station missions lose 10 to 15% of their bone density on average. That level of bone loss is comparable to the deterioration seen in elderly people with severe osteoporosis. The bones become structurally weaker. The risk of fracture under normal activities increases dramatically. Recovery after returning to Earth requires months of physical therapy, and some studies suggest that some bone density loss may be permanent, even after years of rehabilitation on the ground. Muscle mass follows the same pattern of decline. Without the constant work of supporting your weight against gravity, muscles atrophy at a rate that exercise can partially but not fully counteract. Astronauts on 6-month missions can lose up to 20% of their muscle mass, despite exercising 2.5 hours every day, including vigorous resistance training with specialized equipment. The exercise regimes are intense by any ordinary standard. They only partially slow what the body is doing in response to its actual environment. Your body does not care what you want. It adapts to where it is. Cardiovascular changes compound these problems. On Earth, your heart works continuously against gravity to pump blood upward toward your brain. This effort shapes the heart's structure and keeps the cardiovascular system tuned for the demands of standing, walking, and moving against a 1G environment. In microgravity, that effort isn't required. The heart weakens. Its shape changes slightly, becoming more spherical rather than the elongated form it has on Earth. The network of blood vessels in your legs, which on Earth act as a secondary system returning blood upward against gravity through a combination of muscular contraction and valve action, becomes less effective. When astronauts return to Earth after long missions, the sudden demand for their cardiovascular system to operate against full gravity again causes severe dizziness, fainting, and sometimes immediate loss of consciousness. Some astronauts have had to be physically carried off the landing spacecraft because they cannot stand under their own power. Weeks of reconditioning are required before they return to normal cardiovascular function. Vision problems are another consequence that wasn't well understood until relatively recently. Research over the past 15 years revealed that roughly 60% of astronauts on long-duration missions experience significant changes in their eyesight. Some of these changes reverse after returning to Earth. Others do not. The leading explanation is that in microgravity, fluid normally distributed through the body by gravity shifts toward the head. On Earth, gravity draws fluid toward the feet, and the body actively counteracts this. Remove gravity, and that counteracting process overcorrects, and excess fluid pressure accumulates inside the skull. This elevated intracranial pressure appears to change the shape of the eyeball and can cause swelling of the optic nerve. Some astronauts have returned with permanent vision degradation. The immune system is also affected. Studies have shown that immune cells function less effectively in microgravity. Viruses that normally remain dormant in the body, including herpes viruses that the vast majority of adults carry without symptoms, can reactivate during spaceflight. Wound healing is slower. Inflammatory responses are altered. At the same time, the radiation environment of deep space further suppresses immune function through a distinct mechanism. The net result is a crew that is simultaneously more vulnerable to infection and less capable of mounting the normal defensive response. These are the effects documented over 6 months. A Mars mission exposes a crew to microgravity for 12 to 18 months in transit alone, split across 2 legs of the journey. On Mars itself, gravity is 38% of Earth's. That partial gravity might make a meaningful difference for crew health. It might not. No human being has ever spent extended time in a partial gravity environment at that level. Every physiological data point we have comes from either Earth's full gravity or the zero gravity of the International Space Station. 38% gravity is a gap in the experimental record that only going to Mars can fill. It's possible that Mars gravity is enough to substantially slow bone and muscle loss compared to microgravity. It's also possible that there is a threshold below which partial gravity doesn't provide meaningful protection, and that 38% falls below that threshold. In that scenario, astronauts would continue losing bone and muscle mass throughout their stay on the surface, not as fast as in transit, but continuing. By the time the return window opens, 2 or more years into the mission, their skeletons might be so weakened that the physical stresses of launching off Mars, traveling home, and re-entering Earth's atmosphere could cause serious injury. Re-entry from deep space is not gentle. The spacecraft decelerates from roughly 25,000 miles per hour to near zero in a matter of minutes. Even with parachutes and heat shields absorbing most of the energy, the crew experiences forces of several Gs pressing down on their bodies during the most intense deceleration phase. That load, applied to a skeleton that has spent 3 years being progressively weakened, could produce fractures. Not because something went wrong with the spacecraft, simply because the bones can't carry the load. And if they survive re-entry, recovery on Earth could take years. Some fraction of returning Mars crew members might never return to the physical capability they had before departure. This is the honest reading of the physiological data extended to mission durations that no existing study covers. Now, add radiation, which operates silently throughout every moment of the journey and the surface stay, accumulating in ways that only become apparent in consequences that develop slowly and are sometimes irreversible. On Earth, you are shielded from the radiation environment of deep space by 2 overlapping systems working simultaneously. The first is Earth's magnetic field. This field extends from the planet's interior out into space, deflecting charged particles from the solar wind and from cosmic ray sources. It forms a protective bubble called the magnetosphere that shields everything within it from the direct bombardment that space presents. The second is the atmosphere, roughly 60 miles deep. With most of its mass in the lowest layer, Earth's atmosphere absorbs much of the radiation that gets through the magnetic field. The shielding provided by the atmosphere is roughly equivalent to about 10 meters of water in terms of particle stopping power. Together, these two systems reduce the average person's annual radiation exposure to about 0.3 rem from natural background sources. Astronauts on the International Space Station, which orbits within the outer portions of Earth's magnetic field and has the planet itself blocking radiation from below, receive about 15 to 20 rem per year. That's already 50 to 60 times higher than surface exposure. But they're still inside Earth's protective zone. The moment a spacecraft leaves Earth's magnetosphere and enters interplanetary space, that protection is gone entirely. Two categories of radiation then become the dominant hazard. The first is solar energetic particles. The sun occasionally releases massive bursts of high-energy charged particles during energetic events, including solar flares and coronal mass ejections. These solar particle events can deliver very large radiation doses in short time periods, sometimes within hours. A significant solar particle event during a Mars transit could expose crew members to several hundred rem in a matter of hours. At that dose level, acute radiation syndrome develops. Nausea, vomiting, severe gastrointestinal damage, immune system collapse, internal bleeding. At the highest doses, the prognosis without intensive medical intervention is very poor. Spacecraft can be equipped with small, heavily shielded emergency shelters where crew members retreat when a solar particle event is detected. Ground-based monitoring and space weather forecasting can provide warning time, though events can develop faster than predictions. These shelters add mass to the spacecraft. They provide protection against the intense but episodic threat of solar particle events. They do nothing about the second and more persistent radiation threat: galactic cosmic rays. Galactic cosmic rays are high-energy particles, predominantly protons and heavier atomic nuclei, that originate from sources outside our solar system. Supernova remnants, active galactic nuclei, and other extremely energetic astrophysical processes accelerate these particles to enormous velocities, often exceeding 99% of the speed of light. They permeate interplanetary space and travel in all directions, isotropically, filling the space between the planets. What makes galactic cosmic rays particularly difficult to deal with is their energy. These are not like the radiation from a hospital X-ray machine that can be blocked by a lead apron. They're particles carrying orders of magnitude more energy. When a galactic cosmic ray proton strikes a shielding material, it can produce secondary particles in the collision, a shower of lighter fragments that may actually result in more total biological dose than the original particle. This means that simply adding more shielding can make the galactic cosmic ray problem worse rather than better, depending on the material used and the specific particle energies involved. Hydrogen-rich materials like water and polyethylene are more effective than dense metals for galactic cosmic ray shielding because they produce fewer secondary particles. But shielding of any kind requires mass, and mass is the enemy of everything in space travel. Providing enough water-equivalent shielding to meaningfully reduce galactic cosmic ray exposure would require surrounding the crew quarters with many meters of water or equivalent material. The mass involved would dwarf the rest of the spacecraft and make the mission architecture essentially impossible with any propulsion system we currently have. During each leg of the interplanetary transit, with current realistic shielding designs, crew members would receive an estimated 30 to 40 rem of radiation exposure. On Mars itself, where there is no magnetic field, and the atmosphere provides shielding roughly equivalent to about 20 centimeters of water. The estimated annual radiation dose on the surface is around 20 to 30 rem, depending on solar activity during that period. Total accumulated exposure across a 3-year mission, combining both transit legs and the surface stay, runs to an estimated 100 to 140 rem. NASA establishes career radiation limits for astronauts based on age and other individual risk factors. But the general framework, in most practical scenarios, caps lifetime allowable exposure at 100 to 200 rem. A single Mars mission would consume most or all of a crew member's career radiation budget. That's under normal conditions, with no major solar particle events. Long-term health consequences of that level of accumulated exposure are well established in broad outline, but imprecisely characterized at individual level. Cancer risk increases substantially, with estimates suggesting a 20 to 30% increase in lifetime cancer probability above baseline rates. Cardiovascular damage accumulates at the cellular level as radiation disrupts normal cellular repair mechanisms. Cataracts are more common among people with high radiation exposure histories. Central nervous system effects are an area of active concern. Animal studies using simulated galactic cosmic ray environments have demonstrated cognitive changes, including impaired memory formation and altered behavioral patterns in exposed rodents. Whether these effects translate to humans and at what dose levels they become clinically significant is not yet fully understood. The truthful answer is that no human has ever spent 3 years in deep space exposed to unshielded galactic cosmic ray bombardment. The Apollo astronauts who left Earth's magnetic field did so for periods of about a week. International Space Station crews have the longest continuous radiation exposure records for humans in space. But they are still partially protected by Earth's field. We are extrapolating from animal studies, from shorter duration human missions, and from epidemiological data about radiation workers and other populations with elevated exposures. The models are the best available. They may prove accurate. They may underestimate the actual effects. The first extended Mars mission will provide data that no model can fully predict in advance. The fuel problem becomes most acute when you confront what bringing the crew home actually requires in concrete terms. Everything described so far assumes the crew can actually launch off Mars when the return window opens. That requires propellant, a great deal of it. Mars has gravity equivalent to about 38% of Earth's. This makes escaping Mars significantly easier than escaping Earth. But easier is not the same as easy. To reach Mars, orbit from the surface requires achieving approximately 11,800 feet per second of velocity. Then, additional velocity is needed to depart Mars orbit and enter a transfer trajectory back toward Earth. Then, more velocity management is required to enter Earth's atmosphere safely. Each of these maneuvers demands propellant. The Tsiolkovsky equation applies to all of them. Rough estimates for the mass of propellant needed to get a crew off the Martian surface and return them to Earth range from roughly 80,000 to over 150,000 pounds, depending on mission architecture, vehicle design, and trajectory choices. 150,000 pounds of propellant on the surface of Mars. Every pound of that must either come from Earth, shipped during the launch window before the crew departs, or be manufactured on Mars using local resources. Shipping that quantity from Earth has to happen during a preceding launch window, which means years of lead time, enormous additional mass to launch, and complex logistics for landing the propellant safely on Mars before the crew needs it. And there's a problem that sits even further upstream, before any propellant ever reaches Mars at all. Getting a single Starship loaded with enough propellant to leave Earth's orbit and head for Mars is itself an enormous undertaking. Starship burns essentially all of its fuel just reaching low Earth orbit. To go anywhere beyond that, it has to be refueled in orbit by other starships acting as tankers. By current published estimates, fully refueling one Mars-bound Starship requires somewhere between 8 and 12 separate tanker flights, each one launching, rendezvousing, transferring its propellant, and returning. Now, consider a mission architecture that sends 5 starships toward Mars in a single transfer window. That would require somewhere in the range of 40 to 60 launches, all compressed into the roughly 1-month window when Earth and Mars are favorably aligned. No rocket program in history has ever achieved a launch cadence like that. And the orbital propellant transfer that all of it depends on, transferring cryogenic methane and oxygen between 2 vehicles in orbit, has only been tested at very small scale. Moving thousands of tons of supercold liquid propellant between spacecraft, reliably, repeatedly, on a tight schedule, is a technology that essentially does not exist yet at the scale the mission requires. The refueling problem alone could determine whether a given launch window is met or missed. In-situ resource utilization, known as ISRU, proposes to solve the return fuel half of this by manufacturing the propellant on Mars. The Martian atmosphere is approximately 95% carbon dioxide. Mars has water ice in the soil and at the poles. Using a process called the Sabatier reaction, carbon dioxide can be combined with hydrogen to produce methane and water vapor. Electrolysis then splits water into hydrogen and oxygen. The result is methane and liquid oxygen, which are exactly the propellants SpaceX's Starship vehicle uses. The concept is elegant in a way that makes it genuinely attractive to mission planners. You only need to bring hydrogen from Earth. Everything else comes from local Martian resources. SpaceX chose methane as Starship's fuel, specifically because it can, in principle, be synthesized on Mars, allowing the vehicle to refuel for the return trip. The gap between the concept and reliable execution at mission-critical scale is the challenge. The ISRU equipment must be landed on Mars before the crew arrives, because if the return propellant isn't ready when the return window opens, the crew cannot leave. Earth cannot send propellant fast enough to help on any timescale that matters. The equipment must survive landing, which is its own complex engineering challenge. It must deploy autonomously in a Martian environment that no one has prepared for it. It must extract water from Martian regolith, which requires drilling or heating equipment. It must compress and process carbon dioxide from the thin Martian atmosphere, which requires large compressors running continuously to collect meaningful quantities. It must run chemical reactions at the scale needed to produce the enormous quantities of fuel required. And it must do all of this for months to years before any human hands touch it, operating autonomously in an environment that swings between extreme cold and moderate warmth daily, in pervasive fine dust that infiltrates equipment, under cosmic radiation that degrades electronics over time, with no maintenance personnel available. If a pump fails, it stays failed until the crew arrives. If a seal degrades and leaks, it keeps leaking. If dust accumulates on sensors and causes incorrect readings that put the system into an error state, the system stays in that state. Earth knows something is wrong when the propellant production telemetry shows a problem. Earth sends troubleshooting instructions. The messages take 3 to 24 minutes each way. Autonomous systems try to execute whatever workaround is possible. But some problems require physical intervention, and there is no one to provide it. The crew that eventually arrives will check on this equipment that has been running alone for a year or more and see whether their return home is real or hypothetical. A small-scale proof of concept has been demonstrated by the MOXIE experiment aboard NASA's Perseverance rover. MOXIE produced oxygen from Martian carbon dioxide in small quantities, confirming the basic chemistry works in the actual Martian environment. But MOXIE produced oxygen at about 6 to 10 grams per hour during its test runs. Producing the tens of thousands of pounds of propellant needed for a human return mission requires a system operating at a scale orders of magnitude larger, running continuously for months, with the reliability of life-critical equipment. That engineering development has not been completed. The testing and validation required to trust it with human lives doesn't exist yet. Developing that confidence will take years of work that is still ahead. The doubts about whether the current approach can work at all are not confined to cautious commentators. A feasibility study published in a peer-reviewed scientific journal concluded that a crewed Mars mission, built around the Starship architecture as currently conceived, faces fundamental engineering constraints that may make it unworkable in its present form. The analysis pointed to the vehicle's very high dry weight, the mass of the empty spacecraft itself, which eats into the velocity budget so severely that the vehicle may be physically unable to carry out a return flight to Earth. It pointed to the absence of a demonstrated closed-loop life support system capable of sustaining a crew for the full mission. And it pointed to the reliance on in-situ propellant manufacturing, which would require massive surface power generation, almost certainly nuclear, along with water mining infrastructure that is not currently in development. This is not a fringe objection. It's a sober engineering assessment, conducted by researchers at a National Aerospace Institute and published in the peer-reviewed literature, concluding that the most prominent plan for getting humans to Mars and back has not yet closed the gap between ambition and physics. The people behind that plan dispute elements of the critique, as you would expect. But the existence of a serious, peer-reviewed analysis arguing that the return trip may not be achievable with the current vehicle tells you how unsettled the fundamental questions still are. The habitat problem is where the mission's requirements meet the Martian environment most directly, and the environment's hostility becomes most concrete. People need places to live on Mars. Not just survive, though survival is already demanding enough. They need pressurized, thermally controlled, radiation-shielded spaces where they can eat and sleep and work and exercise and maintain the physical and psychological health that keeps a crew functional for years. Prefabricated habitat modules, designed on Earth and packed for launch, can be landed on Mars before the crew arrives. The landing itself is a major engineering challenge. Mars has an atmosphere, which creates aerodynamic heating during entry at high speed and requires heat shields. But the atmosphere is too thin for parachutes alone to slow a heavy vehicle to safe landing speeds. Earth's atmosphere is thick enough that a spacecraft returning from orbit can use a heat shield to absorb the initial deceleration and then parachutes to manage the rest. Mars doesn't offer that margin. You enter the thin Martian atmosphere at hypersonic speed. The heat shield absorbs thermal loads that would incinerate the vehicle without it. And then parachutes can provide some deceleration in the upper atmosphere, but they aren't enough on their own. Retrorocket engines must fire at precise moments to complete the deceleration and manage the final descent. The timing must be correct. The fuel expenditure must be calculated perfectly. The landing site must be navigated autonomously because the communication delay prevents any ground control intervention. By the time Earth receives telemetry indicating that the vehicle has entered the atmosphere, the landing is already complete. For robotic missions, increasingly sophisticated and reliable systems have been developed to handle this. The Sky Crane system that delivered the Curiosity and Perseverance rovers involved a rocket-powered descent stage that lowered each rover on cables, then flew away. For each rover, the entry, descent, and landing sequence worked perfectly. But each rover weighed about 900 kilograms. A habitat module for humans, along with the life support equipment, power systems, and supplies needed for years on the surface, would weigh tens of thousands of kilograms. At that scale, the aerodynamic and propulsive challenges multiply. More mass means more deceleration force needed, which means more retro-rocket propellant, which means more mass, which means more deceleration needed. SpaceX's approach with Starship involves flying the vehicle into the Martian atmosphere under aerodynamic control, and then using the vehicle's own engines for a powered descent to the surface, similar in principle to how the Falcon 9 first stage lands back on Earth. On Earth, this approach has been demonstrated and refined. On Mars, with its different atmospheric density, different gravity, different terrain, and without the benefit of iterative test flights to work out problems, the first attempt will be genuinely uncertain. The engineering effort to develop and validate landing technology adequate for the mission-scale payloads is substantial and ongoing. Assuming successful landing, the habitat must then maintain structural integrity for years in conditions that work continuously to degrade it. The pressure differential between a habitable internal atmosphere and the near vacuum outside creates constant stress on every seam, every seal, every penetration, every window. A small leak that might be a minor maintenance issue in a building on Earth becomes an emergency on Mars, because the thin atmosphere outside provides no reserve of air to replace what's lost. Thermal cycling is another continuous stressor. At the Martian equator, surface temperatures swing from around -100 degrees Fahrenheit or -73 degrees Celsius at night to +70 degrees Fahrenheit or about 21 degrees Celsius during peak afternoon warmth. That's a range of 170 degrees Fahrenheit or about 94 degrees Celsius within a single Martian day. And a Martian day lasts about 24 hours and 37 minutes, slightly longer than Earth's. This thermal cycling causes materials to expand and contract repeatedly. Seals experience this stress daily. Metal components experience it daily. Every mechanical connection, every flexible seal, every structural joint is being cyclically loaded and unloaded day after day for years. Material fatigue under thermal cycling is well understood in engineering. But predicting the long-term performance of specific designs in specific conditions requires either very long-duration testing under realistic conditions or accepting uncertainty. For a Mars habitat, accepting too much uncertainty means accepting risk to the crew. Dust is the environmental feature of Mars that receives the least attention in public discussions and creates the most persistent operational headaches in engineering analysis. Martian dust particles are extremely fine, often in the range of a few micrometers, and electrostatically charged. They adhere to surfaces tenaciously. They infiltrate joints and mechanisms. They coat solar panels continuously and reduce their power output over time. The Opportunity rover, which operated on Mars for almost 15 Earth years, far beyond its intended 90-day mission, was ultimately ended when a global dust storm in 2018 coated its solar panels heavily enough that it could not generate sufficient power to maintain battery charge through the night. For a human habitat that requires vastly more power than a rover, continuous dust management on solar panels would be an ongoing operational requirement throughout the mission. Dust also creates a health concern inside the habitat. Martian dust contains perchlorates, the same toxic compounds found in the surface soil, and bringing dust inside the habitat carries contamination risk. Every airlock entry is a potential contamination event. Decontamination procedures for crew members and equipment returning from outside add operational complexity to every excursion. And global dust storms, which can envelop the entire planet and reduce surface sunlight to a small fraction of normal levels for weeks or months, would force the crew to reduce power consumption dramatically and curtail outdoor activities during the storm's duration. Global storms are not rare. They occur with some regularity during Martian southern summer, and their onset, intensity, and duration are not reliably predictable far in advance. Mission planning must account for them as a normal operational condition, not an exceptional one. Life support for a multi-year Mars mission requires systems that have no direct precedent in human spaceflight. Every human needs roughly 800 grams of oxygen per day. Every human produces roughly 1 kilogram of carbon dioxide per day that must be removed before it accumulates to dangerous concentrations. Every human needs around 2 to 3 liters of water for drinking, more for food preparation and hygiene. Food must deliver roughly 2,000 to 3,000 calories per day in nutritional balance appropriate for sustained health across multiple years, accounting for the elevated caloric demand of physically active work in a pressurized environment and the specific nutritional deficiencies that can develop in people whose food is entirely from stored or artificially grown sources. On the International Space Station, these needs are met through a combination of onboard life support systems and regular resupply missions. The environmental control and life support system on the station removes carbon dioxide from cabin air, uses electrolysis to regenerate oxygen from water, and recovers water from humidity, urine, and other waste streams at recovery rates of around 90 to 93%. The remaining fraction is made up through resupply. The system works, but it requires regular maintenance and periodic component replacement. It was designed knowing that spare parts could be delivered and that technical expertise on the ground could support troubleshooting via real-time communication. A Mars mission cannot rely on any of those safety nets. The life support system must function for the full duration of the mission, with only the spare parts and tools the crew brought with them. Water recovery must approach 100% because there is no regular resupply to compensate for losses. Oxygen generation must be reliable continuously because there is no backup reservoir of air being shipped from Earth. Carbon dioxide removal must work because there is no alternative atmosphere to substitute. Water can potentially be extracted from Martian soil, which contains water ice at various depths depending on latitude. The Phoenix lander excavated ice within a few centimeters of the surface in the high northern latitudes. Extracting that ice requires drilling or heating, which requires energy. Processing it to remove perchlorates and other contaminants requires additional treatment steps. The entire water extraction and processing chain must function reliably as part of the life support system. Food presents its own supply challenge. Packaged food, sufficient for a crew of 4 to 6 people for 3 years, has a mass measured in thousands of kilograms. Growing food inside pressurized greenhouse modules would reduce the mass launched from Earth, but at the cost of additional infrastructure requiring power, water, and volume. Crops grown under artificial lighting in Martian gravity, using processed Martian regolith as a growth medium after perchlorate removal and nutrient supplementation, have different characteristics than crops grown under optimal conditions on Earth. Yields may be lower and less consistent. Crop failure from a fungal outbreak, a pest introduction, equipment malfunction affecting lighting or irrigation, or any number of other causes would create a gap in nutrition that the stored supply must cover. The stored supply is finite, and power is the foundation all of this sits on. Every life support process requires electricity. Carbon dioxide scrubbing requires power. Water electrolysis requires power. Lighting for crops requires power. Water extraction from regolith requires power. Communication systems require power. Heating the habitat through Martian nights requires power. Solar panels on Mars receive only about 43% of the solar intensity that panels on Earth receive, because Mars is farther from the Sun. Dust accumulation continuously reduces that percentage further. During global dust storms, solar energy availability collapses to a small fraction of already reduced baseline levels. Nuclear fission reactors would provide consistent, reliable power regardless of dust and weather conditions. NASA's Kilo Power project developed prototype reactors capable of providing about 10 kilowatts of electrical power from compact uranium-fueled designs. 10 kilowatts is a starting point for a small crew. A fully operational base requires more. Multiple reactor units, larger designs, or a combination of nuclear and solar power would be needed. Developing and validating nuclear power systems for Mars deployment involves regulatory pathways around launching nuclear materials on rockets, which add time and political complexity to mission planning. These are not impossible obstacles. They are real ones, with their own schedules that don't necessarily align with mission timelines. The communication gap between Earth and Mars is not a minor operational inconvenience. It's a fundamental condition that changes the entire character of how the mission must be run. The speed of light sets an absolute maximum rate for information transfer. A signal sent from Mars to Earth must cover whatever distance currently separates the two planets, and at about 186,000 miles per second, the minimum one-way travel time is roughly 3.5 minutes, occurring when the planets are at their closest. The maximum, when they are on opposite sides of the Sun, is about 24 minutes. The round-trip delay, therefore, ranges from about 7 minutes at best to about 48 minutes at worst. These numbers define the responsiveness available to a crew encountering any problem that might benefit from Earth support. Imagine a scenario where a component of the life support system begins showing anomalous readings. The crew identifies the issue and sends a detailed description to Mission Control. 7 minutes pass before Earth receives the message. Engineers consult, diagnose, and compose a response. Another 7 minutes before the crew receives it. The response requires clarification about one specific reading. Another exchange. If the problem is evolving in real time, if air quality is declining or pressure is dropping, the crew cannot wait for ground support to iterate toward a solution. They must act with their own knowledge and judgment. This is why the training requirements for a Mars crew are categorically different from anything required for missions that operate with real-time communication. Every crew member must be capable of independently diagnosing and responding to a wide range of system failures. Not just operating systems under normal conditions, understanding them deeply enough to recognize novel failure modes, improvise solutions from available materials, and make judgment calls under pressure that would normally be escalated to specialists. Medical competency is where this requirement is starkest. On Earth, medicine is deeply specialized. The physician who treats a cardiac emergency is not the same one who treats a dental abscess, and neither is the one who addresses an orthopedic injury. Specialization works because specialists are accessible. On Mars, the medical capability the crew has is exactly the capability they brought. At a minimum, one crew member should be trained to near physician level across a broad scope of emergency and internal medicine. All crew members should have substantial practical medical skills. The ability to perform basic surgical procedures, to manage acute medical emergencies, to administer anesthesia when needed, to handle obstetric emergencies if the crew includes people who could become pregnant. Medical conditions that would be managed straightforwardly in an Earth hospital become potentially catastrophic on Mars, not because they are more severe medically, but because the resources for managing them are exactly the resources that were deemed affordable to transport. Appendicitis requires surgery. A crew member with appropriate training could perform an appendectomy in a properly equipped habitat medical bay. But complications that would normally trigger specialist consultation must be managed with the knowledge available in the room. Post-operative infections require antibiotics. If the specific antibiotic needed wasn't in the supply, an alternative must be identified from what is available. A serious dental abscess can progress to systemic infection. Systemic infections in people whose immune systems are already compromised by radiation and microgravity effects can escalate faster than in healthy people under normal conditions. Chronic conditions that develop unexpectedly during the mission have no specialist referral pathway. If a crew member develops arrhythmia or a metabolic condition or an autoimmune flare, management depends on what was brought and what the crew knows. Every medical decision is made by people who are also dealing with their own physical stress, potential fatigue, and psychological strain, without the ability to consult a specialist who examined the patient in person. The psychological dimension of the mission is, in some ways, the least precisely quantifiable and possibly the most important to get right. Humans are social animals, shaped by millions of years of evolution for living in communities with dozens to hundreds of individuals, with rich variety of social interaction, access to varied environments, and the ability to move away from sources of stress. A Mars habitat violates essentially all of these evolutionary expectations simultaneously and continuously. The habitat is small. The crew is small. The same walls, the same spaces, the same view outside, the same routines, every day for years. The same few people at every meal, every work session, every recreational hour. There is no escape from the group because there is nowhere to go. There is minimal, genuine privacy. There is no broader social world to retreat into when the immediate social environment becomes difficult. Research on analog environments has been specifically motivated by the need to understand how people behave under these conditions. Antarctic winter-over crews are the most commonly studied. Submarine crews provide another dataset. Dedicated isolation facilities, where groups spend months in confined conditions, have been used to simulate aspects of deep space missions. The findings are consistent across contexts. In the early period of isolation, motivation is high, group cohesion is strong, and participants report high satisfaction with their work. This is followed by a period where the novelty wears off and the unchanging nature of the environment settles in. Minor irritations accumulate. Habits that were easy to overlook early on become sources of genuine friction. In an ordinary social environment, you dilute minor interpersonal irritants by having many other relationships. In a group of 6 people on Mars, that dilution isn't possible. The 6 people are the entire social world. Research on Antarctic winter-over crews documents a dip in morale that appears reliably in the middle of the isolated period, sometimes called the third quarter phenomenon. Groups that navigate it successfully develop explicit coping strategies and norm-setting behaviors. Groups that don't navigate it can experience serious interpersonal dysfunction. In Antarctica, the winter ends. The ship comes. People leave. On Mars, no ship comes. The group must find its way through whatever interpersonal landscape develops and maintain functional working relationships, because every member of the crew is essential to mission success, and there is no option to remove anyone. You cannot fire someone on Mars. You cannot reassign them to a different project. The crew that departed Earth is the crew for the mission. This means that the selection process for Mars crews must optimize not just for individual excellence in their technical domains, but for the specific combination of people who can share a small space for years, maintain productive relationships under stress, and resolve conflict constructively when it inevitably arises. Group compatibility is harder to assess than individual capability. The chemistry of a particular group of people in a particular confined environment over a particular duration cannot be fully simulated in advance. The best ground-based analog studies are approximations. They provide useful information, but they're not predictions. The people who end up on the first Mars missions will have been as carefully selected and prepared as any group in the history of exploration, and they will still encounter psychological terrain that no amount of preparation could fully map. On top of all the interpersonal dynamics is the existential weight of the situation itself. Earth is far away and getting farther for the first months of the mission. Communication with family is asynchronous, with delays measured in minutes. Real-time conversation with the people you love is not possible. You send a message and wait hours for a response that might trigger another exchange, another wait. The people and places that defined your life are on the other side of an interplanetary void. For the first period after arrival, there is still the excitement of being somewhere new, of doing something unprecedented. Then Mars becomes ordinary. Not in a bad sense necessarily, but it is just life. And life on Mars is small, enclosed, demanding, and isolated in a way that has no equivalent in human experience. The people who will handle this best are not simply resilient in the general sense. They are people for whom the meaning of the mission is so clear and deeply held that it provides genuine stability through the hard periods. People who find the work itself satisfying enough to sustain motivation across years of routine. People whose connection to each other can withstand the strain of constant proximity. And people who have made genuine peace with what they left behind. not suppressed the grief of it, made peace with it. That is a specific kind of person. They exist. The scale of applications received by the Mars, one program, which despite collapsing as an organization received over 200,000 applications when it opened recruitment in 2013, demonstrates that a substantial number of people genuinely want this. Not people who haven't thought about it carefully. People who read what it actually means and said yes anyway. Those are the people who will make Mars work. Funding and political continuity are forces that operate behind all the technical challenges and shape everything about how fast the problems get solved. Sustained programs require sustained budgets, and sustained budgets in democratic systems require sustained political support across time periods that typically span multiple administrations with different priorities. The Apollo program succeeded partly because it was a focused sprint with a clear political mandate, a specific goal, and a deadline that the most visible figure in American public life had committed to publicly. Meeting that deadline required concentrating resources at a level the program has never seen before or since. NASA's budget peaked during the Apollo era at nearly 4.5% of the total federal budget. Today, it operates at around 0.5%. The arithmetic is not subtle. Mars missions are not a sprint. They are a development program spanning decades. The technology development, system testing, crew training, mission preparation, and operational execution of the first Mars mission will collectively require sustained investment and sustained political will across a longer time horizon than any previous human spaceflight program. Programs that require that kind of continuity are vulnerable to cancellation, reduction, or redirection with each change of administration. The Constellation program, designed to return humans to the Moon as a step toward Mars, was terminated in 2010 after spending over $9 billion. Not because the technical approach was fundamentally wrong, because the political and budget environment changed. The Space Launch System that succeeded, it flew its first unmanned test in 2022, more than a decade after program start, and has faced sustained scrutiny about cost-effectiveness relative to commercial alternatives. Commercial programs, particularly SpaceX's Starship, represent a genuinely different approach to the economics of getting mass to orbit and to Mars. Starship is designed specifically with Mars colonization in mind. Its propellant choice, its scale, and its architecture are all shaped by what a Mars mission requires. The technical progress on Starship is real and substantial. The timeline from current development stage to a system that can reliably deliver a crew to Mars and return them safely is still measured in years of work remaining. And priorities can shift even within a single program. In early 2026, SpaceX itself chose to redirect its near-term focus away from Mars and toward lunar missions, partly because Starship had been selected as a lunar lander for the Artemis program, and partly because the hardest Mars-specific technologies were proving slower to mature than hoped. That decision pushed the Mars timeline out by years in a single announcement. It's a reminder that even the most committed organization, with enormous resources and a founder who has spent decades advocating for Mars specifically, adjusts its schedule when the engineering reality demands it. This isn't a criticism of the program. Ambitious aerospace development always takes longer than initial projections, because ambitious aerospace development always encounters problems that weren't fully anticipated. And the correct response to encountering unexpected problems is to solve them, not to ignore them, and stick to a schedule. But it does mean that the optimistic timelines, stated at press conferences, need to be understood as aspirational targets rather than reliable predictions. More resources, more testing, more parallel development paths, all of these accelerate the work. Less of any of them extends the timeline further. The funding reality shapes risk tolerance as well. When budgets are constrained, missions have to accept more risk to stay on schedule. Shielding is sized to what's affordable rather than what would be ideal. Spare parts manifests are trimmed to reduce mass. Backup systems are fewer than engineers would prefer. Medical supply lists are negotiated against payload capacity. These trade-offs are real, and they affect how safe the mission actually is. More investment doesn't make the physics easier, but it does make the engineering more thorough, the testing more comprehensive, and the margin for the crew wider. There are problems we haven't fully solved yet, that we're still in the process of discovering. This is one of the features that makes the Mars challenge consistently harder as time passes, rather than easier. The human body in space is not a static research subject. Every long-duration mission adds to the dataset. And the dataset keeps revealing things that weren't previously understood. The vision problems associated with intracranial pressure changes weren't recognized as a significant issue until the growing body of ISS data made the pattern clear. The detailed immune system effects of microgravity are still being characterized. The interaction between the different physiological stressors, where bone loss and immune suppression and radiation effects and cardiovascular deconditioning combine in ways that may not be simply additive, is an area of active research. Synergistic effects, where two stressors together are worse than the sum of their individual impacts, are notoriously hard to predict. And we know that 3 years in the Mars mission environment is a qualitatively different exposure than anything studied so far. The longest continuous spaceflight on record was 437 days by Russian cosmonaut Valery Polyakov on the Mir space station in the mid-1990s. He returned to Earth and underwent rehabilitation. But 437 days is about 15 months. A Mars mission is roughly 3 years, more than twice as long. Whether the physiological effects at 3 years are simply twice the severity of 15 months, or whether they are qualitatively different in ways the shorter duration doesn't reveal, is something we cannot know with certainty until people spend 3 years in those conditions. The research programs designed to answer these questions are ongoing and producing important results. ISS has been an invaluable platform for exactly this kind of investigation. The Human Research Program within NASA exists specifically to characterize and mitigate human health risks in space. Progress is being made, but the timeline of research findings and the timeline of mission schedules are not always synchronized. Decisions about when to attempt a crewed Mars mission will be made before all the relevant biological questions are answered. That is an unavoidable feature of pushing into genuinely new territory. It means accepting that some of what happens to the crew will be discovered as it happens to them, not predicted in advance. The landing problem deserves one more look, because earlier we treated it as part of getting the habitat to the surface. And there's a dimension to it that only becomes clear when you think about it as an acute event rather than a general engineering challenge. Mars entry, descent, and landing happens in a window of minutes. You go from interplanetary cruise speed to a soft touchdown in the time it takes to make a cup of coffee. During those minutes, thousands of things must go right in sequence, and nothing can wait for a ground controller to intervene. The minimum communication delay from Earth is over 3 minutes. By the time a landing signal is even received on Earth, the outcome has already been determined. Everything has to be handled by the vehicle itself, in real time, with no possibility of help. The heat shield either holds or it doesn't. The parachutes either deploy at the right moment or they don't. The retro rockets either fire with the right timing and thrust or they don't. The navigation system either steers clear of boulders and slopes and craters or it doesn't. Each of these has to work, in order, autonomously, on a schedule determined entirely by physics. And here is what makes the human version different from every robotic landing that has come before. Every successful Mars landing in history has carried instruments and rovers, hardware. If a robotic landing fails, an expensive machine is lost, and the mission planners grieve it and learn from it. A crewed landing carries people. The same few minutes, the same autonomous sequence, the same physics, but now with human lives riding on every step working correctly the first time, in conditions the vehicle has never actually been tested in. There are no second attempts at a landing. There is no abort to orbit once the descent has begun. You commit, and the sequence either delivers you to the surface or it doesn't. That is why the first crewed landing on Mars will be watched with a level of tension that very few human achievements have ever generated. There's something about this whole problem that doesn't appear on the engineering diagrams, and it shapes everything about the practical path to Mars. History. The problem of sending humans to Mars is not a new one. It has been seriously proposed, seriously funded in preliminary ways, and seriously attempted in terms of planning for over half a century. Understanding why it hasn't happened yet requires understanding that history, not as a list of failures, but as a record of how our understanding of the problem has evolved. In the 1960s and early 1970s, the vision of sending humans to Mars was widely shared and seemingly close. The Apollo program had demonstrated that humans could leave Earth's immediate vicinity, travel to another world, land, survive, work, and return. The technology worked. The organizational capability existed. The only question seemed to be whether the political will and funding could be sustained. Numerous serious proposals were developed in this period. Some involved massive vehicles using nuclear propulsion, building on the nuclear thermal rocket research that had demonstrated in laboratory testing that nuclear-heated propellant could achieve roughly double the efficiency of chemical rockets. Others involved fleets of chemically propelled spacecraft assembled in Earth orbit. Mars mission planning documents from this era describe timelines for the first crewed landing in the 1980s, or at latest, the early 1990s. These weren't fringe proposals from enthusiasts. They were engineering studies conducted by people who had just put humans on the moon. Then the Apollo program ended earlier than planned, for a combination of budget pressures and shifting political priorities. The focus of NASA moved to the Space Shuttle program, which promised a different vision of the future, one based on routine, low-cost access to Earth orbit rather than bold exploration of deep space. Mars missions remained on paper and in the minds of people who cared about them. Periodically, they would resurface in public discussions. A detailed study called the Space Exploration Initiative in 1989 proposed returning to the Moon and then going to Mars on a 90-day timeline for response. The cost estimate was enormous, the political support was insufficient, and the initiative faded. The human exploration of Mars. Study in 2000 was another serious technical effort that produced detailed mission architecture documents. The vision for space exploration announced in 2004 proposed returning to the Moon by 2020 and using that as preparation for eventual Mars missions. Constellation was the program built to execute that vision. It was cancelled in 2010. Artemis succeeded it, with different architecture, and eventually a first crewed lunar orbital mission flown in 2022, and a first crewed lunar landing still in development. As of today, Mars comes next. In every plan, it's always next. The most recent chapter of this story belongs to SpaceX, and it follows the same pattern with remarkable precision. Elon Musk, first publicly committed to landing on Mars in 2018, proposing back in 2016 to send a capsule to the surface within 2 years. That mission never happened. The target was revised to 2022, this time using the still-developing Starship. That date passed without the mission. By 2024, the target had moved again to an uncrewed mission in the 2026 window, with crewed flights potentially following around 2028 to 2030. The pattern across this entire sequence is almost mechanical. A bold Mars timeline is announced roughly 5 years out. Substantial but incomplete progress is made on the prerequisite technologies. The announced date arrives without the mission. A new target is set for the next transfer window. And then, in February of 2026, came the clearest illustration yet of why this is so hard. SpaceX announced it was delaying its Mars ambitions by roughly 5 to 7 years, redirecting its engineering and financial focus toward lunar missions instead. The crewed Mars target that had been floated for the late 2020s effectively slid into the early 2030s. Not because the company gave up, because the prerequisite technologies, the orbital refueling, the reliable heavy landing, the propellant production, turned out to need more time than the optimistic schedule allowed. This is the thesis of everything we've discussed tonight, playing out in real time. The date moves because the problem is genuinely, physically, this hard. The timeline shifts. The architecture changes. The commitment fluctuates with political winds and budget environments. But the destination remains the same. And crucially, with each serious planning cycle, the engineering understanding has deepened. Each time engineers sit down to work out how to actually do this, they understand it better than the previous team did. The challenges look different now than they did in the 1970s. Not harder in the sense of the physics being more demanding. The physics hasn't changed. Harder in the sense that we now know much more precisely what we're dealing with. We know about the radiation environment from spacecraft that have measured it continuously. We know about the physiological effects from astronauts who have lived in space for months. We know about the dust dynamics from rovers that have operated on the surface for years. We know about the atmospheric variability from decades of surface measurement. Each of these knowledge advances is genuinely valuable. You cannot engineer solutions to problems you don't understand. But each advance also reveals that the problem has more layers than previously appreciated. This is the pattern. Better understanding, revealing greater complexity. It's not unique to Mars. It's the normal experience of anyone who has seriously engaged with a genuinely hard problem. The problem was always this hard. We're just now understanding it clearly enough to see exactly how hard. One area where that deepened understanding has had the most impact is the question of what happens to human health over truly extended periods in space. The International Space Station has been continuously occupied since November of 2000, making it the longest-running continuous human presence in space in history. More than 2 decades of data. Dozens of crew members who have spent 6 months or more aboard. A smaller number who have spent close to a year. Russian cosmonaut Mark van der Hey spent 355 days aboard the station in 2021 to 2022, the longest single-mission spaceflight by an American astronaut. Scott Kelly and Mikhail Kornienko spent 340 days on the station in 2015 to 2016, specifically to study the physiological effects of extended spaceflight, with Scott's twin brother Mark Kelly serving as a ground-based control subject. The data from these extended missions has been invaluable, and some of what it has revealed has been sobering. The bone and muscle loss continues more or less linearly with time, not tapering off as some had hoped it might. Some physiological adaptations that were thought to be problematic only in the short term have turned out to persist or worsen over longer missions. The vision changes associated with intracranial pressure have been found to affect more crew members and to persist longer after return than initially observed in shorter missions. Cognitive effects, including performance changes on standardized tests of attention and executive function, have been documented in crew members toward the end of long missions. The immune changes become more pronounced with mission duration. Scott Kelly's Year in Space generated detailed data comparing his physiology to his genetically identical brother on the ground. The findings were complex. Some changes were dramatic. His telomeres, the protective caps on chromosomes that shorten with aging, actually lengthened slightly during the mission, counterintuitively. His gut microbiome shifted significantly. Gene expression patterns changed in thousands of genes. Cognitive performance on certain tests declined. Most of these changes reversed relatively quickly after return to Earth. Some didn't. A year of spaceflight left physiological fingerprints that hadn't been there before. For a 3-year Mars mission, these fingerprints would be deeper. How much deeper, we don't know. The data from 1-year ISS missions doesn't linearly predict what happens at 3 years. The body continues adapting as the mission continues. Some adaptations may reach a stable state. Others may continue to evolve in potentially problematic directions. This is genuinely uncertain territory. And the uncertainty matters because the decisions being made about when to attempt a crewed Mars mission will be made before this uncertainty is fully resolved. The propulsion challenge, independent of the fuel manufacturing problem on Mars, is worth exploring in more detail because the technology choices made in this area shape everything else about the mission. Chemical propulsion, burning fuel and oxidizer in a combustion chamber to produce thrust, is what every crewed spacecraft ever launched has used. It's mature, reliable, well understood, and relatively simple in engineering terms. It's also operating near the limits of what chemistry can provide. The best chemical propellant combination currently in common use is liquid hydrogen and liquid oxygen. This combination offers a specific impulse, the measure of propellant efficiency, of around 450 seconds. Specific impulse measures how much thrust you get per unit weight of propellant consumed per second. Higher is better. SpaceX's Starship uses methane and liquid oxygen because methane can be manufactured on Mars, as previously discussed. The specific impulse of methane oxygen is around 350 to 370 seconds, slightly less efficient than hydrogen oxygen, but the Mars ISRU advantage more than compensates for this in a mission context. Nuclear thermal propulsion takes a fundamentally different approach. Instead of chemical combustion, a nuclear reactor heats propellant to extremely high temperatures, causing it to expand and exit through a nozzle at much higher velocity than any chemical reaction can achieve. Higher exhaust velocity directly translates to higher specific impulse. Nuclear thermal rockets, tested during the NERVA program in the 1960s and early 1970s, demonstrated specific impulse values of around 800 to 900 seconds, roughly double the best chemical systems. What this means in practical terms is that a nuclear thermal rocket can achieve the same velocity change as a chemical rocket while using less than half the propellant mass. In the context of the rocket equation, halving propellant requirements is enormous. It doesn't just reduce the amount of propellant you need. It reduces the mass you need to accelerate, which reduces the fuel for that acceleration, which reduces the mass further. The advantages compound. For a Mars mission, nuclear thermal propulsion would allow faster transit times on more propellant-efficient trajectories, reducing crew radiation exposure during transit, reducing the physiological impact of extended microgravity, and making the mission architecture more manageable across many dimensions simultaneously. The technology was ground-tested and proven to work. The NERVA program ran prototype engines successfully on test stands in Nevada during the 1960s and early 1970s. The engines worked. It was never flown in space, cancelled partly because the Mars missions it was intended to support never came together, and partly because of concerns about the political optics of launching nuclear reactors. Developing nuclear thermal propulsion for human spaceflight today would require restarting that development thread, designing updated engine configurations, developing flight qualification procedures, navigating the regulatory pathway for launching nuclear reactors, and conducting the testing necessary to establish the reliability required for crewed missions. Estimates for this development timeline run to roughly a decade of serious investment. It's not quick. But the benefit to Mars mission architecture would be transformative. NASA has had ongoing programs aimed at nuclear thermal propulsion development under various names and funding levels. The consistent pattern is that the funding and priority haven't been sustained at the level needed to see the technology through to flight-ready status. Ion propulsion, another alternative, uses electrical power to accelerate propellant ions to very high velocities. The specific impulse of ion drives can reach thousands of seconds, far above both chemical and nuclear thermal systems. The limitation is thrust. Ion drives produce very low thrust levels, meaning they accelerate slowly. This makes them excellent for long-duration missions, where continuous gentle acceleration is acceptable. For human Mars missions, where the crew is being exposed to radiation during transit and needs to minimize transit time, the weeks or months required to spiral up from Earth orbit on an ion drive makes it impractical as the primary propulsion for the departure and arrival phases. Ion propulsion is used effectively on robotic missions. For humans, faster is necessary. The propulsion landscape today is essentially limited to chemical rockets for crewed missions, with nuclear thermal propulsion as the most promising near-term improvement if it can be developed and qualified for flight. What that means is that the transit times and the physiological consequences of those transit times are largely fixed by currently available technology. Changing them requires developing the nuclear option, which requires time and investment that haven't yet been committed at the necessary level. The economic structure of a Mars mission is worth examining as its own subject because it's one of the least glamorous aspects of the challenge and one of the most determinative of whether and when it happens. A Mars mission is expensive, not in a vague sense, in specific, quantifiable ways. The mass that needs to reach low Earth orbit before departure represents dozens of heavy-lift rocket launches. At current prices for the most cost-effective heavy-lift options, each launch costs several $100 million to several $1 billion depending on vehicle and configuration. 30 or 40 launches over several years represents tens of billions of dollars in launch costs alone, before accounting for spacecraft development, habitat development, propulsion system development, life support system development, ground infrastructure, crew training, mission control operations, and all the other elements. Total mission costs for the first crewed Mars landing mission, in any architecture that mission planners have seriously developed, run to hundreds of billions of dollars. This is a level of spending that no single nation's space program has sustained outside the context of an Apollo-scale political mobilization. The Apollo era was unusual. A specific historical moment created specific political conditions that made funding at that level possible. The conditions that created Apollo were not permanent, and they haven't recurred. Commercial space has changed the economics of getting mass to orbit significantly. SpaceX's reusable Falcon 9 has reduced the cost of reaching low Earth orbit dramatically compared to the expendable rockets that preceded it. Starship, if it achieves the reusability and cost targets SpaceX has projected, could reduce costs further still. These reductions matter. They don't eliminate the cost of a Mars mission, but they change the arithmetic in meaningful ways. A mission that costs $200 billion on expendable rockets might cost dramatically less on fully reusable commercial vehicles at the costs SpaceX is targeting. Whether those targets are achieved, and when, is itself uncertain. Starship development costs money. The infrastructure for manufacturing methane propellant on Mars costs money. The habitat systems cost money. The medical capability costs money. Every element of the mission has a price tag, and the total across all elements is large. The funding model matters as well. Government programs funded through annual appropriations are vulnerable to year-to-year political changes. A program that requires 15 years of sustained investment can be set back years by a single, unfavorable budget cycle, because stopping and restarting development work is expensive and time-consuming. Commercial investment operates differently. SpaceX has invested in Starship using a combination of NASA contracts, private capital, and revenue from existing launch business. This makes the program less dependent on any single year's political outcome. But it also means that the mission architecture and timeline are influenced by business considerations as well as engineering considerations. The combination of government programs with clear missions and commercial programs with different incentive structures creates a complex landscape for Mars mission development. Getting to Mars probably requires elements of both. Government provides the mandate, some of the funding, and the regulatory framework. Commercial provides the launch economics and potentially the vehicles. The integration of these two streams, with their different timelines, different decision-making processes, and different risk tolerances, is itself a challenge that the people working on Mars missions have to navigate. The sequence of events leading up to actually landing humans on Mars will require a series of precursor steps that each represent substantial engineering efforts in their own right. A crewed Mars mission doesn't happen without first establishing that the critical components can work. That means landing large masses on Mars, because no element of the human mission can proceed without having demonstrated the ability to get big payloads to the surface safely. Current robotic landers top out at about a metric ton. Human missions need to land dozens to hundreds of metric tons. The technology gap is large. It means testing life support systems for long durations in relevant conditions. The International Space Station has provided extensive data, but there are aspects of Mars life support, particularly water and air recycling at the high levels of reliability needed for a mission with no resupply option, that haven't been fully demonstrated. It means demonstrating ISRU propellant production at something approaching mission-relevant scale. Small lab experiments and MOXIE-scale demonstrations are useful data points, but the mission-critical system is many orders of magnitude larger and more complex. It means sending crewed missions to the lunar surface and using them to test systems and procedures in an environment where Earth is close enough to permit rapid return in emergencies, before committing to a mission where no such return is possible. Artemis aims to return humans to the Moon, partially for this reason, to validate hardware and procedures in a more accessible location before attempting Mars. Each of these precursor steps has its own schedule. Each of those schedules is subject to the same forces that have extended every previous Mars mission timeline. Funding pressures, technical challenges that reveal themselves as work proceeds, regulatory processes, the coordination required between different programs and different organizations. The cumulative effect is that the gap between the earliest credible crewed Mars landing estimate and the actual date of that landing has historically been measured in decades. Programs planned to take 15 years have taken 25. Programs that seemed close have been overtaken by program changes. The people who have been working on this problem the longest tend to be the ones who offer the most conservative timelines. Not because they're pessimistic, but because they've seen the pattern repeat enough times to calibrate their expectations accordingly. None of this means it won't happen. It means it will happen when the sum of technology readiness, funding, political will, and organizational execution reaches a threshold that hasn't yet been crossed. That threshold is real. It's approached by a trajectory that's real. The people doing the work are real. The hardware under development is real. The science that underpins the mission planning is as solid as physics gets. It will happen. But the date on which it will happen is not simply a matter of ambition. It's determined by the intersection of all the forces described over the past hour, in ways that can't be fully controlled from any single vantage point. There's a particular kind of honesty required when discussing the first people who will actually go to Mars. Not the fictional astronauts of movies who face dramatic dangers and overcome them with ingenuity, just in time. The real people, who will spend months inside a spacecraft smaller than most apartments, who will watch Earth shrink from a planet to a point of light, who will land on a world that no human has ever stood on, with no certainty about what the experience will reveal about what they don't yet know, who will live and work and deal with interpersonal friction and health concerns and technical problems in an environment where there is no easy out, and who will do all of this knowing with specificity, because they will have been trained exhaustively, exactly what it will cost them. The physiological effects are real. and they will experience them. The radiation exposure is real, and it will accumulate in their bodies. The isolation is real, and it will be felt. The uncertainty about some elements of crew health is real, and they will be living through the experiment that resolves that uncertainty. They know all of this. They go anyway. The reason they go is not that they've assessed the risks and concluded that everything is acceptable. Some of the risks are significant, and they know it. The reason is that they've weighed what they're risking against what they'll be doing and concluded that the doing is worth the cost. That's not a calculation anyone can make for anyone else. It's the specific determination of a specific person who has spent enough time with both sides of the equation to know what they've decided. The history of exploration is full of people who made that calculation about destinations that at the time represented the extreme edge of what was reachable. Expeditions to the Arctic and Antarctic were deadly for many participants. Early aviation was extraordinarily dangerous. High-altitude mountaineering has claimed many lives. Each of these domains is now understood more safely than in the early years because the early participants gathered knowledge with their lives and bodies that made it possible to do better subsequently. Mars will be similar. The first crews will teach the next ones something that no amount of ground-based research and simulation can fully provide. The accumulated cost of that learning is real. So is the accumulated benefit. By the time humanity is sending its 5th or its 50th crewed mission to Mars, the things we learned from the first ones will have improved every element of the mission. The life support will be more reliable. The radiation shielding will be better understood. The landing technology will have been refined through repeated use. The psychological preparation will draw on actual experience from actual crews. The medical protocols will be based on what actually happened rather than what was modeled. That learning has a price. The people who go first pay a portion of it. They know this, and they go. It is not possible to think about this with full clarity and not feel the weight of it. There is one more challenge that often gets overlooked in the engineering discussions, and it might be among the most practically significant for actual mission planning. The question of what humans actually need to be productive on Mars over multi-year timescales. Not just alive, productive. Because a crew that is alive but incapacitated by physical decline, psychological stress, or medical problems isn't accomplishing the mission. They're surviving. And survival alone, while obviously necessary, is not the objective. The objective is for trained people to do meaningful scientific and engineering work, to build and operate systems, to make good decisions under uncertain conditions, and to lay the foundation for whatever comes after them. That objective places demands on the mission that go beyond the minimum requirements for keeping people breathing. Cognitive performance in space changes in ways that are only beginning to be well characterized. Studies on ISS crew members have used standardized cognitive assessments throughout missions to track how performance changes over time. The findings are nuanced. Some cognitive functions remain relatively stable or even improve slightly during the early part of missions, possibly due to the novelty and heightened engagement of the environment. Others show gradual decline over the course of long missions, particularly in measures of attention, processing speed, and certain aspects of executive function. These changes are modest in absolute terms during 6-month ISS missions. They're manageable. For a 3-year Mars mission, the question of whether modest decline observed at 6 months continues, stabilizes, or reverses over longer durations is not yet answered. Fatigue, accumulation over multi-year missions, is another open question. Chronic fatigue is a known problem in long-duration, isolated environments. Antarctic winter-over crews report it. Submarine crews report it. ISS crews report it, particularly toward the end of long missions. Chronic fatigue doesn't just make people feel tired. It impairs decision-making, increases error rates, reduces motivation, and degrades interpersonal relations. A fatigued crew making decisions about systems that keep them alive is a more vulnerable crew than a rested one. Managing fatigue requires adequate sleep, genuine downtime, meaningful variety in work, and psychological support. All of these requirements compete with the operational demands of the mission for time and resources. A habitat that provides minimal recreational space because volume and mass were constrained. A schedule that leaves little genuine downtime because there's always something that needs to be done. An environment where psychological variety is limited to what can be provided through digital media and communication from Earth. These trade-offs are real, and their consequences are real. The sleeping arrangements on a Mars spacecraft and habitat are not a minor quality of life consideration. Adequate sleep is a physiological requirement as fundamental as adequate food. Disrupted sleep impairs cognitive function, immune response, hormonal regulation, and emotional stability. In the confined, artificially illuminated environment of a Mars habitat, maintaining healthy sleep patterns requires careful design. Circadian rhythm, the biological clock that regulates sleep and wakefulness, is entrained primarily by light. In a habitat where daylight doesn't naturally follow a 24-hour cycle matching human biology, and where artificial lighting is the primary light source, maintaining proper circadian regulation requires deliberate light management. The Martian day is 24 hours and 37 minutes. Almost exactly Earth's. That's fortunate, and mission planners intend to synchronize habitat lighting to Martian local time rather than Earth time. But during dust storms, when natural light is minimal, even if windows or light tubes were part of the habitat design, maintaining artificial circadian lighting requires power. And power, again, is not unlimited. The physical environment of the habitat itself affects crew well-being in ways that compound over time. Confined spaces without natural views create psychological strain, even in people who are tolerating the confinement well, in terms of mood. Access to outside light, even through small windows, matters. Being able to see a natural environment, even an alien one, matters. The design of early Mars habitats will be heavily driven by mass and structural constraints. Large windows are heavy and structurally complex. They represent potential failure points in the pressure envelope. But windows that give the crew a genuine view of the Martian landscape, with its dramatic terrain and two small moons and stars unfiltered by a thick atmosphere, could be among the most important contributions to long-term crew psychological health that the habitat designers can include. The trade-off between engineering conservatism and psychological need is one that will be negotiated in the design process. The outcome matters. The question of who goes is as important as the question of how to get there, and it deserves to be stated directly. The selection criteria for the first Mars crew will be the most demanding in the history of human spaceflight. Not because NASA or any other organization has decided to be exceptionally rigorous as a matter of philosophy, because the actual requirements of the mission demand it. A crew member who develops a serious chronic condition 6 months into the surface, stay cannot be evacuated. A crew member who experiences a severe psychological crisis cannot be removed from the habitat. A crew member who cannot get along with the rest of the crew cannot be replaced. The mission carries who it carries, for the full duration, with the characteristics those people actually have. This means the selection process must get it right in ways that have more permanent consequences than any previous crew selection. Technical excellence is the baseline. Every crew member must bring deep expertise in at least one domain critical to mission success. Piloting, engineering, life support systems, geology, medicine, communications. And every crew member must have broad competency across multiple domains, because there isn't enough room on the mission for narrow specialists who can't adapt. Physical fitness is required not just at departure, but in terms of physical resilience that can be maintained under adverse conditions for years. The people who lose the most bone density and muscle mass on the ISS are not those who exercise the least. Some people respond more severely to microgravity stress than others. Identifying people with physiology that is more resilient to the specific stresses of the Mars environment is part of the selection challenge. Psychological resilience is required, but not the kind measured by how well someone tolerates acute stress. Acute stress tolerance is relevant, but relatively common among people who pursue careers in high-stakes fields. What's needed is the ability to maintain motivation, positive interpersonal relationships, and sound judgment across years of monotony, discomfort, uncertainty, and occasional, genuine crisis. That's a different thing. It's rarer. Identifying it reliably requires more than a psychological evaluation. It requires observing people in extended high-fidelity simulations, in isolated environments for extended periods, and in situations that reveal how they actually behave under sustained pressure rather than acute stress. Social compatibility within the specific crew is essential and cannot be assessed by evaluating individuals in isolation. The chemistry between a specific set of people in a specific confined environment over a specific duration cannot be fully predicted, but it can be approximated through extended group-based training and assessment. The people selected for the first Mars crew will not simply be the best individual candidates. They will be the best group whose collective characteristics make them likely to succeed as a unit across the full duration. That may mean passing over individuals who score higher on technical metrics in favor of groups that score higher on cohesion and compatibility metrics. The mission requires both, but the unit that actually goes to Mars is a group, not a collection of individuals. The ethical dimensions of the first Mars mission are worth acknowledging, even in a discussion that's been primarily about engineering and physiology. The people who go to Mars will be knowingly accepting health risks that are not trivial. Radiation exposure that exceeds career limits under normal guidelines. Physiological effects that may be permanent. Psychological strain that is unprecedented in duration. Medical risks in an environment with limited capability to manage them. These are not trivial costs. They are accepted voluntarily by people who understand what they're accepting in pursuit of an objective they've chosen. This is a form of human agency that has a long history in exploration and in other high-risk endeavors. People accept significant risks for meaningful objectives. We recognize this in mountaineers and fighter pilots and deep-sea divers and emergency responders. The Mars crew is accepting risks of a similar character, though of greater magnitude. The ethical framework that governs this acceptance involves informed consent voluntary participation, meaningful purpose, and organizational support in minimizing risks to the degree possible. All of these elements will be present for a Mars mission. What will also be present is a level of uncertainty that can't be eliminated by even the most thorough preparation. Some of what happens to the first Mars crew cannot be predicted. Some of the medical consequences can't be fully anticipated. Some of the psychological effects can't be fully modeled. Some of the technical failures can't be foreseen. The crew accepts this uncertainty along with everything else. And the organization sending them has an obligation to have genuinely done everything possible to understand and reduce the risks before people's lives are committed to the mission. That obligation is what makes the timeline matter, not just as an organizational preference, but as an ethical requirement. Sending people before the technology is adequate, before the biological questions are answered well enough to prepare them, before the systems have been tested rigorously enough to be trusted, would be failing that obligation. The people working on this understand this. The best of them hold themselves to a standard where the question isn't just whether the mission is technically possible, but whether it has been made as safe as the current state of knowledge allows. That standard is what keeps driving the timelines out when new information reveals something that wasn't previously understood. It's the right standard. The universe doesn't provide easy access to other worlds. It provides physics, and physics has the rules it has. The sun will not let the planets be any closer than they are. Gravity will not accept less fuel to overcome it. The radiation environment of interplanetary space will not reduce its intensity to accommodate human biology. The Martian atmosphere will not thicken itself to make landing easier. All of it is what it is. And what it is happens to be very, very demanding. Over 50 years of serious work and planning and analysis have revealed, in progressively sharper detail, exactly how demanding. The people doing that work are not deluded. They are not ignoring the obstacles. They are solving them, one at a time, in the sequence that the dependencies demand, across a timeline that the scale of the challenge requires. The difficulty is real. The progress is real. The destination is real. When the first crew lands on Mars, it will be an achievement that carries every calculation that got harder and every problem that revealed another underneath it, and every timeline that moved because the engineering turned out to be more complex than the previous estimate allowed. It will carry all of that and be worth it. Some things are worth being hard. Some destinations justify the distance. Mars has been waiting. It will keep waiting. As long as it takes for us to be ready to go there honestly, with clear eyes about what we're attempting, and with the technology and the people to give it a real chance. That's what sending humans to Mars keeps being. Not impossible. Just precisely, exactly, the right amount of hard. If this is the kind of deep dive that keeps you up at night, a like or a subscribe keeps this channel going and means more of them coming your way. Good night.